Sorry, I could not record till now. Okay. So when all the elements in any, okay, so the third method was to multiply the given characteristic equation by s plus a. So s plus 1 into so on, and then get an characteristic equation, and then again follow the same procedure by writing the row array table and finding the solution. So this was one of the difficulty. Then case number 2. So what is case number 2? When all the elements in any one row of the row array is 0. So when you come across such a case where, see here, we have a problem, example problem, where you can see that the entire row has become 0. So when we come across such a case, so this is one more type of difficulty which we have to come across. So in such a case, what is the solution? It has only one solution. The polynomial where coefficients are the elements of the row just above the row of zeros in the row array is called as auxiliary polynomial. So you have to see which row has become all zeros, okay, and you have to concentrate on the row right above that, right above the all zero row. So you have to take this and write these elements in the form of auxiliary equation. Okay, the order of auxiliary polynomial is always even. So here we have the order of the auxiliary polynomial is always even. So this should be taken care of. Okay, I will tell you. We will discuss it when we are solving the problem. So here we have s power 6 plus s power 5 plus 5 s power 4 plus 3s cube plus 2s square minus 4s minus 8 equal to 0. So here you can just write down as it is. So 1, 5, 2 and minus 8. Then we have 1, 3, minus 4 and 0. So when you see this, see in gate problems, when they ask you, they will give you this characteristic equation, and they will ask you whether they'll give you four options, whether it is stable or unstable or marginally stable or whatever it is. So you can see here, whenever actually we get such a solution where all the elements are 0, usually we will get the roots or the poles on the imaginary axis. Whether it is repetitive or non-repetitive, that we can find out only when we find out the solution via this auxiliary equation. But whenever you form the Routher table and see that the elements, you get one row where all elements are 0, usually the solution will be, the poles will be present on the imaginary axis. Okay, but you can see here, there is a negative value, there's a constant value minus 8. So that minus 8, when I write it here in the first column of the Routher table, obviously the system becomes unstable. And if at all the roots or poles are present on the imaginary axis, we will not call that system as unstable system. We call that system as marginally stable system, isn't it? So these are some of the very minute things which you have to really take care. Okay. So here, since we have minus 8, we can easily call the system as unstable. Do not come to a conclusion that just by seeing this row of all elements zeros, you should not come to the conclusion that this system is marginally stable. No. Now you can see that there is one negative term here in the first column. So even if you have all the elements of this row as 0, still the system becomes unstable because of this negative value which is present here. Okay. So now what is that we have to do now? So first two rows we were able to compute. Then find out the other elements. Similarly, 1 into 5 minus 1 into 3 divided by 1 will give a value of 2. 1 into 2 minus 1 into minus 4 divided by 1 will give a value of 6. Then 1 into minus 8 minus 1 into 0 divided by 1 will give a value of minus 8. And 0, because we do not have next elements here, because we have all 0 elements here, so this becomes 0. Then we have this row comprising of 2, 6, minus 8 and 0. So no problem. This is fine. When we compute the next row, 2 into 3 minus 1 into 6 divided by 2, we will get 0 here. 2 into minus 4 minus 1 into minus 8 divided by 2, 0. 2 into 0 minus 1 into 0 divided by 2, 0. And the next consecutive elements are not present here, so this becomes 0. So now we got this row to be all zeros. So when we get zeros, what is that we have to do? We have to immediately consider the row above all zero row. So here you have 2, 6, minus 8 and 0. And these elements, using these elements, we have to form the auxiliary equation. And remember, the auxiliary equation is what? The order of the auxiliary polynomial is always even. So here, consider the auxiliary equation as a by a of s. So a of s is equal to 2 into s to the power 4 plus, don't write this as 6s cube. I told you that it should be even powers. So even reducing power. So here, so this will be now 6s square minus 8s to the power 0. So that will become 1. Okay. So you have to, now this will become our auxiliary equation. Then next step, what is that we have to do is we have to differentiate this auxiliary equation and equate that to 0. So here d by ds of a of s is equal to, so when you differentiate this, you will get 8s cube plus 12s, and that you have to equate it to 0. So you just have to differentiate this only once. Okay. So now when you do that, whatever values you get here, see, you can observe here what is that I've written. This all zero row elements should be now replaced with this auxiliary, differentiated auxiliary equation. So here I will write s cube again. Okay, I will write it as s cube. Don't write it as s square. I'm going to just replace this, or you can just erase the values here, but I don't want to do that. So I've just written again. I've written down here as s cube, and in place of this 0, I will write it as s because it is 8s cube. Then plus 12. So here you will be replacing this 0 with 12, and the rest all will be just zeros because you do not have any other terms here. So just write it as 8 s cube, and then it is 12 and 0 0. Now again you have to follow the normal way of finding out the other elements of the other rows. So here to get this, now to get the s square, the element of this, so what is that you do? 8 into 6 minus 2 into 12 divided by 8. So when you do that, you will get the answer as 3. Then again 8 into minus 8 minus 2 into 0 divided by 8. So you will get the value as minus 8. And 8 into 0 minus 2 into 0 divided by 8. Again you will get a value as 0. And there are no other cross elements here, so this will be 0. Then to get this term, 3 into 12 minus 8 into 8 divided by 3. I've written down as it is. And when I solve this, I will be getting some positive number. Okay. Even you can try this and see. So when we do that, we'll get a positive number here. 3 into 0 minus 8 into 0 divided by 3 is 0. And the rest all, since we have zeros here, we will get these values or these elements also to be zeros. And then this, how do we write? We just write down directly from this characteristic equation along with the sign, very important. So it is minus 8. So when we do that, you can see that all the elements of the first column are positive numbers except this one. So this is a negative value. And from positive, how many sign changes are happening here? From positive, we have negative. And after that, we do not have any sign changes. So there is only one sign change. So only one sign change. So one pole is in right half of S plane to make the system unstable. Okay. Just a minute. Okay. So this was about the case 2. So I hope now you are familiar with case 1 and case 2. So case 1 we have 3 different methods, and case 2 we just have one solution. If you want, I will repeat it. Do you want me to repeat this? You can just put a message in the chat and tell me if you want me to repeat this. Okay, fine. Okay, fine. So let us move on with other examples. Okay. So I'll just move with other examples. Okay. So these are some of the other problems. Let's see how these problems are solved. So now, so this was the one which we have discussed already. So there is a characteristic equation which is given here. Okay. So how was that done? The route array for the given characteristic equation is formed. So this is a very basic problem. So here we are going to observe the sign changes. So they're all positive and they're all greater than zero. So all the roots of the characteristic equation are present in the left half of S plane. So that was one of the problems. Similarly, we have one more example problem. So here you can see whenever you come across such values 2, 4, and if you find that there is a common term, then you can divide that by 2 so that your simplification becomes much more simpler. Okay. And here you can see in the first, observe the first column, you have a negative sign here. So this indicates that the system is unstable. And how many sign changes were there? There were two sign changes in the first column. So how many roots are present on the right half of explain? Two roots, and the system is unstable. So similarly, we have one more problem, a simple problem. This is just, so here what is that he says? As there is no sign change in the first column of this table, there is no root present on the right half of this plane. Here there is a mistake. The given system is stable. So be careful when you come across such problems. Here they have mentioned wrongly. It is a stable system. Okay. Then, excuse me. Okay. Now they will give you question like this. Determine the stability of the system whose overall transfer function is given by, below. C of s by R of s is equal to 2s plus 5 divided by s power 5 plus 1.5 s power 4 plus 2s cube plus 4s square plus 5s plus 10. So as I told you, the poles are, we derive the poles from the denominator polynomial. So here the characteristic equation you have to, they have not given the characteristic equation directly. So from this equation, you have to take the characteristic equation and equate that to 0. So here the denominator polynomial should be considered and that should be equated to 0, isn't it? So what is that he has told? If the system is found unstable, how many roots it has with positive real part. So whenever you have a positive real part, that means the roots are present on the right half of S plane and that indicates that the system is unstable. So here he is saying that if the system is found unstable, then how many roots, how many sign changes will indicate how many roots are present on the right half of S plane. Okay. So here the characteristic equation is given by, so s power 5 plus 1.5 into s power 4 plus 2s cube plus 4s square plus 5s plus 10 equal to 0. Now write down the route array table by alternatively writing down the values for the first row starting from the first element. So this is 1, 2, and 5 in the first row, 1.5, 4, and 10 in the second row, and then equate these equations. You don't know how to write down these elements. This into this minus this into this divided by this. So in the same way, you have to compute for the other elements of the table. So if you see, you are getting a negative term here, which indicates that the system is unstable. And how many sign changes are happening? From positive to negative and from negative to positive, and the rest all remains positive. So there are two sign changes. So it is concluded that the system has two roots with positive real part. Therefore, the given system is unstable. Correct? So this is one way of asking the question. And see here, we have one more example. A feedback control system has a characteristic equation s power 6 plus 2 s power 5 plus 9 s power 4 and so on. So how many poles are on the left half of S plane, on the imaginary axis, on the right half of S plane? So again what you have to do, consider the same equation, start writing down the table for this. So as you can see here, using the formula we have found out, and you can see that all these elements have no issues in the first column. But this one has all zeros, isn't it? So the auxiliary equation you have to consider. How do you consider? So let us stop at this point and consider the auxiliary equation and then continue with the problem. Okay, that is how they have done. So here the auxiliary equation you have to consider for the elements given here 1, 8, 16. So and remember, very important, the order of the S should be even, isn't it? The auxiliary equation is given by auxiliary equation s power 4 plus 8s square plus 16. Okay, so d by ds of, you have to now differentiate this once. So when you differentiate this once, you will get this value as 4s cube plus 16s. So now what is that you have to do? Here, now wherever you have the zero element, you have to replace that with the values of this differentiated equation. So the zeros in s cube row are now replaced by the coefficients of coefficients 4 and 16. So this will become 4, this will become 16, and the rest all will be zeros, and then we have to proceed as it is. So now the route array then becomes like this, isn't it? So you will get the route array like this. So when you get the route array like this, I told you, then you can see wherever you have the common terms. If this is optional, you can just divide that by those values. So here 4 is common, so divide by 4. Okay, and retain, so this will be 1 and this will be 4, 0, 0, and find out the rest of the other values by doing this. 1 into 16 minus 4 into 4 divided by 1. 1 into 0. Okay, sorry, this is not the one. So this is SQ. 1 into 8 minus 1 into 4 divided by 4. 1 into 16 minus 1 into 0 divided by 1. This, you will get this value. So like that you have to find out and see the common. So divided by 4. So you'll get S square as 140. And again you can see that again you are getting one more row with all zeros. So again, what is that you have to do? Again, consider the elements above this row. So it is 1 and 4. Write down the auxiliary equation. So this becomes what? S square plus 4, isn't it? And then differentiate that once. So you'll get the answer as 2s. So now the zeros in S row are now replaced by the coefficients of the coefficient 2. So you can see here the route array then becomes what? This becomes 2 and this becomes 0. And then this will be what? This will be just what? You can see in the problem the last value. Where is that? Okay. Okay. So they have taken this, I guess, if I'm correct. They have considered that and they have written down s power 0 as s power 0. Where is that? Written that as 4. 4, and then here we have no other value, so 0. So now you can consider the first column of the entire route table and all the values are positive. So here what is the conclusion they have written? As there are no sign changes in the first column of the table, there are no roots in the right half of S plane. So when there are no roots, as I told you that whenever we encounter a route table with all elements as zero, I mean with a row, with one single row of all zeros, then we have to write like this. When simple roots are present on the imaginary axis, the system time response will have continuous sustained oscillations. So to determine the frequency of these oscillations, solve for the root of auxiliary equation. So how to solve for the roots of auxiliary equations here? So this is the auxiliary equation that you consider. Put s square as x. So you get this equation like this. Solve for this quadratic equation. You will get x as minus 4 minus 4. So x we have taken as s square. So what will be s square now? S square is equal to minus 4 minus 4. It will be plus or minus j2 comma plus or minus j2. So now if you observe, there are repeating poles on the imaginary axis. So as there are no sign changes in the first column of the table, there are no roots in the right half of S plane. So 4, but 4 roots will lie. 4 roots. This is plus J2 minus J2 plus J2 minus J2. Though they are present on the imaginary axis, but still you can see that they are repeated. They are repetitive, isn't it? So you are getting repetitive poles on the imaginary axis. Four roots will lie on the imaginary axis. Two roots will lie on the left half of S plane. Okay. As the roots are repeated on the imaginary axis of S plane, system will become unstable. So these are some of the important things that you have to remember. So there are some problems which you will not expect what will be the end solution just by seeing the characteristic equation. Okay, so that was one of the problem. So similarly, here also they have asked for characteristic equation below, determine the number of roots with positive real parts. Same way. So here you can see we have just encountered a single zero element. So when we come across such a route array table, then we have to use any one of the methods which we have discussed in case one. So they have taken this method where x is replaced by 1 by z. Simplify, form the route array table again, find out the answer, look for the sign changes, and then indicate how number of sign changes corresponds to the number of real parts. So this is one such other problem. Okay, I think you can do these sort of problems now. Okay, let's see some other variation. Now we will take up this one problem. The characteristic equation for certain feedback control system is given below. So in each case, determine the range of value of k for the system to be stable. So these are one of the most important problems which they will ask you. Even in gate problems, you can come across such problems, and even in university question paper, these are the kind of problems which will be asked. Okay? So you have to determine the range of k for the system to be stable. So write down the route array table as it is. So s power 4, s cube, s square, s power 1, s to the power 0. So 113, k1, 0, 436, 0, 0. Okay. Then here there is a common term, so I've just divided it by 4. So now find out the values of the next other rows. So here you will get 4 into 13 minus 1 into 9 divided by 1 as 4. 1 into k1 minus 1 into 0, which is 0, divided by, what is this, divided by 1. So you will get the value as k1, and these are zeros. Similarly, now consider this 4 into 9, 36, minus 1 into k minus k, or k1, anything is fine, divided by 4. The rest all will be zeros. And here the final whatever value you have, you can just write down as k. So this is k1, this is k1 here, k1, k1, k1. So now what is that we have to do now? What is that we see? We see that no elements here are 0, so that is satisfied, but we have to see to it that all the elements should be greater than 0. So what we do, we have to consider now this term, we don't know whether it is greater than 0 or less than 0. So now consider this should be greater than 0. So for system to be stable, 36 minus k divided by 4 should be greater than 0. And also this term, k1 should also be greater than 0. So solve for that. So when you do, so you have got one minimum boundary where k should be greater than 0. And what about this? This you will get k should be less than or equal to, so here less than, this should be less than 36. K should be less than 36. So the range of k will be, k should lie between 0 and 36. It should be greater than 0 but less than 36. Isn't it? So less than or equal to 36. But here they're talking for the stability of the system. So stability of the system, even if you get 0 here, we have the alternative methods. That's why they have taken the range as k greater than or equal to 0 and less than or equal to 36. Therefore, the range of K for stability is 36, sorry, K1 greater than or equal to 0, less than or equal to 36. So such kind of problems will be asked. So here also, I think this you can try. I will share this, this material is already shared with you, I guess. If not, I will share it with you. And some other problems will also be shared with you, okay? So this is about, this is how you have to do. So B1, I've read just written it as B1 because it's a very huge equation which we could not write it yet. So they have represented by B1 and they have written separately what B1 is. So with this, you can see that there are, this is how you have to find out the range. So you will get for all different conditions, you have to write down greater than 0, greater than 0, greater than 0. And then you have to find out what is K here, what is K here, and what is K here. And then together combine, you have to combine and you have to come with a conclusion what should be the range of K. Okay, and also you can even comment on the stability of the system based on the sign changes in the first column. Okay, so these are many various other problems which you can try to do.